Meteoroids, meteors, and meteorites are essentially the same object at different stages of their journey through space and entry into Earth's atmosphere. A meteoroid is a small piece of rock or metal that travels through space. They can be as small as a grain of sand or as large as a boulder, and they are typically remnants of comets or asteroids. When a meteoroid enters the Earth's atmosphere, it begins to heat up and create a bright streak of light. This is what we call a meteor, or a shooting star. Bolides are large meteors that are much brighter than typical meteors. They can be brighter than the sun and can even cast shadows. Most meteors burn up completely in the atmosphere and never reach the ground. However, some meteors are large enough to survive the journey through the atmosphere and hit the Earth's surface. These are called meteorites. On average, meteoroids enter the Earth's atmosphere at speeds ranging from 11 kilometers per second to 72 kilometers per second, which is significantly faster than the speed of sound. The speed of sound at sea level is only around 0.34 kilometers per second. Meteoroids travel fast because they are in orbit around the sun, like the planets. When a meteoroid enters Earth's atmosphere, it is moving at high speed relative to the Earth's surface. The meteor traveling at hypervelocity speeds encounters the gases in the atmosphere, which cause friction, compression, and ionization. This results in the meteoroid's kinetic energy being converted into heat energy, causing the meteoroid to heat up rapidly and develop a glowing plasma around the meteoroid. Meteors begin to glow or light up in the Earth's atmosphere at an altitude of around 80 to 120 kilometers above the Earth's surface. The exact altitude at which a meteor begins to glow can vary depending on factors such as the meteoroid's size, velocity, and angle of entry into the atmosphere, as well as the atmospheric conditions at that particular location and time. When a meteor enters the mesosphere, it encounters dense air molecules that create significant resistance to its high-speed movement. This resistance causes the meteoroid to decelerate rapidly, converting its kinetic energy into heat energy through ablation. As the meteoroid decelerates, it compresses the air molecules in front of it, creating a high-pressure shockwave that travels through the atmosphere. This shockwave moves faster than the speed of sound in the surrounding air, which results in a sonic boom. Light travels faster than sound, so you'll see a meteor fireball before hearing it. The delay in sound during a meteor fall can vary due to factors like distance, altitude, and atmospheric conditions, typically ranging from seconds to minutes or even longer. Let's listen to the real sound of a meteor crashing through the Earth's atmosphere. The following is the real sound of the pressure waves generated by the hypersonic flight of the Chelyabinsk meteor, which fell over Russia in 2013. As the meteoroid slows down, the surrounding air cools the meteoroid. This cooling process occurs through conduction, where the heat energy is transferred from the meteoroid to the surrounding air molecules. Eventually, the meteoroid reaches a point where the deceleration and cooling cause it to reach its terminal velocity. At this point, the meteoroid's speed stabilizes, and it continues to descend at a constant velocity. Once it hits the ground, it becomes a meteorite. Meteorites can exhibit a wide range of temperatures upon impact. Some meteorites are so cold that they can form frost from the surrounding humidity upon hitting the ground, while others may be just warm to the touch or even hot. The actual temperatures reached by meteorites upon impact depend on factors such as size, composition, entry angle, and velocity, and can be difficult to determine with precision. Meteorite-strewn fields are formed when a large meteoroid or asteroid breaks apart in the atmosphere before reaching the ground, scattering numerous fragments over a wide area. These strewn fields can cover several kilometers in diameter depending on the size and composition of the original meteoroid. The distribution of meteorites within a strewn field is not always uniform. Factors such as the angle of entry, the speed of the meteoroid, atmospheric conditions, and the nature of the impact can influence where the fragments ultimately fall. As a result, meteorites within a strewn field may be clustered or scattered over a larger area. Larger meteoroids retain momentum and can impact the ground with force. The intense energy generated upon impact can cause the meteoroid to vaporize into gas, resulting in a large explosion that generates a powerful burst of energy and shock waves, which can have significant effects on the surrounding environment. If a meteorite strike is large enough, it can radically deform the rocks, sand, or soil around the point of impact. The terrestrial materials near or beneath an impact site are physically altered by the tremendous heat, pressure, and shock waves associated with very large meteorite impacts. These transformed terrestrial materials are known as impactites. One example of an impactite is Australasian tektites. These tektites are formed from the terrestrial molten fragments ejected out of a crater after a large meteor impact. Australasian tektites are named after the Australasian strewn field, which covers 10 to 30% of the Earth's surface. Tektites from the Australasian strewn field can be found all over Southeast Asia, and even as far south as southern Australia. Recent findings have suggested that the impact event that created the Australasian strewn field tektites originated from an impact event that occurred in southern Laos, where a crater lies buried below the Bolaven Plateau around 790,000 years ago. Can you imagine a meteor impact with so much energy that ejected molten glass was raining down all over Indochina, the Philippines, and as far south as Australia?